Hello, everyone. Thank you for joining us today in this new Rhino user webinar. I am Guillermo Varela from Enil Europe. I am here today with Arsenii Bychkov from Powerhouse Company. Arsenii is an architect and computational designer, and he will show us how they modeled the wooden landscape of the KJ Den Haag residential tower with Rhino and Grasshopper from early design sketches through construction. Remember that in the last 15 minutes of this webinar, we will have some time for answer your questions, so you can ask them in the chat and we will check them at the end. And also, I would like to mention that the webinar is being recorded and will be available on our YouTube channel, where you can find more webinars and tutorials. Thanks again to Arsenii and Powerhouse Company for their interested in presenting this webinar. And let's start with the presentation if you're ready, Arsenii. Thank you.
Thank you so much, Guillermo. Thanks for the introduction. So hi, everyone. My name is Arsenii. I'm indeed an architect and a computational designer working for a Dutch office, Powerhouse Company. And today I'm going to be talking about one of our projects, which is called KJ Den Haag. And its very special feature, a complex double curved timber ceiling, and how we designed it from concept and brought it to construction site. I'm going to start with a small introduction about our office. Once again, our office, Powerhouse Company. This is a Rotterdam-based office. We're located in this lovely floating building, which you can see on the image on the right. We are a team of almost 100 architects with actually another office is located also in Germany, in Munich, in Oslo, and in Nairobi. And here I am among the Powerhousians. I'm doing here architecture, mainly in the concept phase. I'm also doing computational design, and I am a huge fan of Rhino and Grasshopper, and I'm also very happy to be here and tell a little bit more about our project. Powerhouse is mainly busy with public projects of different scales. We've done the Library of Rotterdam. We're designing stadiums sometimes. Also, we do quite a bit of different residential buildings on different scales, from large-scale towers to small-scale, very sustainable buildings like you see on the left. This is our recently completed project in Rotterdam, actually, which is a social housing, which is completely made out of wood. So you can see that in our portfolio, the main topics are sustainability, circularity. We're focusing on the quality of living, on the quality of working in the space. But of course, now and then, there is a project that requires a bit more complexity in it. And that's why we also have quite a bit of different computational projects in our portfolio. And one of those projects, which is kind of heading the completion this year, I think, maybe next year, is called KJ Den Haag. That's the one that you can see on the left. KJ Den Haag is a residential tower. It's actually this kind of twin tower project, which is located in The Hague. It has roughly 48,000 square meters of residential program, and it also has this beautiful, vast landscape, wooden landscape on the ground floor, which serves as a public program of this building. Basically, the idea behind the project is that it stands in front of the central station of The Hague, and it serves as the main entrance, like the new main entrance point and an exit point for the central station. So it invites all the guests who are coming to The Hague and shows them this is kind of the first thing that they see when they're entering The Hague. And that's why this kind of very special feature of the project was created. This 9,000 square meter wooden ceiling, which is spanning over the whole ground floor and is lifting up to almost, I think, 70 meters. And it's covering and hosting multiple public program functions like shops, small cafes. The idea of the ceiling, it came from the coastal landscape of The Hague and was directly inspired by the dunes. Hague is quite famous for the dune coast that is actually quite close by to the city center. And we kind of wanted in this project to bring this idea of dunescape to the city center of The Hague, so that the people that are entering the city, they immediately see this very important and key feature of The Hague right in front of them, actually right above them. That was initially our ambition, as you can see here on this axonometric view. The 9,000 square meter double curved freeform surface, which formed this very complex dunescape, let's say. You can also see this kind of points where the ceiling is touching the ground. Those are called the cones. We have 4 of them, and that's where the main public program is actually located. These cones are serving as the entrance point to the building, to the residential program, to the towers, and also to the cafes, to the shops that are located on the ground floor. And from these cones, the ceiling is kind of rising in this very nice curved shape and forms this wooden dome above the heads of people who are coming to visit The Hague. From the point of view of the structure, this ceiling is made completely out of wood. It has 2 main construction principles behind it. There is a back structure, so sort of a substructure, which is made out of wooden planks. And right on top, on the image that you can see on the right, we're positioning the smaller planks, sort of like wooden slats, that are covering this back frame and creating a nice continuous shape. So this project is, as I mentioned already, is actually facing completion quite soon, hopefully. And that's why I thought it could be nice to actually tell a little bit more, and I thought it might be quite an interesting topic to explain how this project came to be. The reason is that here on the left, you can see a conceptual sketch, which I found in some folders of our project, which is dating back to 2016, when the project was still in the competition phase, and then the competition was won by Powerhouse. It was made in Rhino 5, and it's like quite a nice image, but of course it looks like a very conceptual image. And of course, ideally, in an ideal world, this image is directly translated to the construction site. But we all know that the real world scenario works in a bit of a different way, and usually this process of bringing the project from the concept to the construction site is a very difficult challenge, and it has a lot of complications on the way, and you can go off route. So basically, the perfect solution for such complex shape projects, in my opinion, are usually building some sort of feedback loops where the initial concept is informing the detailed design, while the detailed design at the same time is informing the concept. And of course, there is, in my opinion, no better tool for such thing, for building this sort of feedback loops, as Rhino and Grasshopper. Basically, what we did for this project over the time of its development, so I would say over 10 years, although I've been working on it mainly for the past 4 years, when the project was facing kind of the final stages, we've created a sort of a mini toolbox of different mini scripts combined into larger scripts in Grasshopper that allowed us to maintain this feedback loop over the whole process of developing the project. And I'm going to just dive into each category of this mini toolboxes that we've created to maybe show you a little bit more how it was working, and also to explain a little bit more which tools were useful and how we kind of faced the different challenges that were coming towards us. The 3 categories that I'm going to talk about are, the first one is shape manipulation, which included the surface, the kind of the basic surface construction, and the discontinuity analysis. So basically the check of how well the curved surface is behaving, if there are any kinks, if there are any edges or breaks. And that's, of course, a bit closer to this conceptual phase. Then there was the kind of realization and bringing to the construction site, where we're going to talk a little bit about the planks division, how the extreme curvatures were analyzed, and how the clashes were checked using Rhino. And there is an extra category, which is a bit of a secret now, but I hope we have enough time for it so that I can show what we did there. So the first category, the shape manipulation, basically came down to, first of all, building the shape. The surface of the ceiling started as this type of a ruled surface, double curved ruled surface, which was later combined together with the cones, which were kind of projected on the ground floor. And from the ground floor, these curves kind of blended seamlessly into this ruled surface shape. And from there, the two main parts of the ceiling were developed, the so-called wall part, which is also known as cone, and the horizontal part, the ceiling part, which has just horizontal planks going in a single direction. And another point here was the discontinuity analysis, and that basically has something to do with the fact of how complex the shape is. The thing is that the shape that we've built was quite difficult to actually analyze and visualize. We couldn't usually tell if there were any creases in this shape, and even 3D printing some pieces of it were not helping because it was such a massive surface. I'll just put it to, oh, sorry, damn it. It was such a massive surface that it was very difficult to actually trace. The scale was not enough at our home-based 3D printer. So we came up with this idea of treating the surface as an actual landscape and doing the isocurves analysis, so-called. So basically just projecting the isocurves and kind of splitting the whole complex surface into elements, which really helped us to understand where we have the discontinuities, the creases, and optimize the shape later so that it's kind of just one smooth wooden landscape above us. Okay, so we're going to dive a little bit into Rhino, and I'm going to just show really quickly how this all came to be. In this first category, let's say. So here I have our massive script, and this was, let me just quickly hide the guests. So this is something that we started with. We just had, oh, sorry, that was the final result actually. This is something that we started with. We had the kind of the main building already designed on top of the ceiling. And then there was just kind of the base ground floor, which served as a guideline to what was supposed to be built. What was really helpful in the very beginning. So we started with creating this ruled surface. I'm going to try to, yeah, just a second. There we go. Yeah, perfect. So basically, this was the very beginning of the project. We had this very nice ruled surface with the boundary curves, which were forming kind of the shape, which were shaped in the form of the building, the way the plan worked. These are in red, and then the blue ones and the white ones were actually the ruling curves that allowed us to build this initial complex shape. What was really, really nice here that we could, of course, easily manipulate different aspects of this initial surface. And then, of course, that would become the part of the script from the very beginning and would go till the very end, so that once we, for instance, start doing the planks, we can already see all those changes in the model. One of the crucial elements, for instance, for creating this complex shape was the way the curve actually connects to the boundary curve, the boundary curve in red over here. So, for instance, we could, yeah, oh, I need to see that window actually. So we could kind of do different types of connection, and that would, of course, affect how the building looks. And it will instantly, of course, rebuild the whole shape. And it might take a while. Hopefully it doesn't take too long. Yeah, and then it would affect, for instance, now it kind of created this horrible dip here, which we really don't want. So I'm going to just Control Z this one. And then the next step, as I showed in the presentation, was actually, let's see. So the next step was, if we hide this one for now, taking this initial shape and merging it together with the cones, with the shapes that you see on the ground. So basically, this curves that you see on the ground here and there, they are the bases of these 4 curves that we used to highlight the main position of the entrances to the buildings or entrance to the office parts of the building. Or for instance, here it was an entrance to the bike parking that is located under the building. And what we created was basically a small tool that allowed us to merge these curves seamlessly with the surface of the ceiling above. How did we make it? Well, we used the 2 curves on the ground. One was kind of highlighting the point where the cone would land. And the other curve, the larger one, was actually highlighting the point where, highlighting the position of the curve where the cone will meet the top surface. In 3D, it actually kind of looked like this. So what we did, we projected these curves, the outer curves, towards on the ceiling over here. And it allowed us to create this very nice, lovely mushroom shape. And this process was actually repeated for each one of these cone elements. And the way we also controlled it was quite nice because, of course, we wanted to have a bit more control over how this shape is developing. And in order to do so, some extra curves were created. Mainly, there was one curve right in between them, which was actually just using a very basic tweening tool in between the bottom curve and the top curve. And what this curve did, it kind of was once again just projected towards the top ceiling surface. However, it was used as sort of a tangency point for the cone surface to be developed. So for instance, if I will just increase this slider by 26 points, we'll see what will happen. Yeah, so the surface will just become way more tight. And this will, of course, has some sort of results later in the design. So that's how we were able to basically control the shape of each cone and see how tight it will be, like what sort of shape it will create, and so on and so on. And as I said, as I mentioned already, we've created this thing for every single cone. Let's see how it looks. So basically, after creating these cones, we were happy with this result. And then later, this surface, we took some of the cutouts that were coming from the ground. Those were the curtain walls that were heating the surfaces. These were some of the points where we actually didn't want to have any wooden planks. So basically just small optimizations. And we just cut them through and we came to sort of a final surface that became the ceiling. So as I said, also, there was one crucial point behind how we wanted to analyze the shape. The complexity of the surface didn't really allow us to see how well it was connecting, especially in the points where the cone was meeting the horizontal surface. So what we tried to do, we tried to find a way to see if there are any creases here, because we know from experience, or like we knew from experience, that those will be extremely visible once they're built. So initially, of course, we tried, and I will show this on an already baked surface. So initially, of course, we just tried to go with a ready-made tool for that, which is the surface and then environment map. And while it was kind of working, it still wasn't really giving us the precision that we wanted, especially considering the fact that, I'm just going to try to hide this thing. Yeah, perfect. It wasn't really giving us the precision that we wanted in terms of defining which point exactly is not matching here. And like if there is a smaller crease or if there is a smaller break or something like this. So it all looked nice, but we were not convinced. So basically, a very simple solution came to us, and that was basically making this. Oh, just a second. Basically, just using the contour tool over the surface of the ceiling, so literally treating it as a landscape. And if I will turn it on right now, we'll see what it produces. It basically produced this lovely graph, and using the discontinuity node and kind of highlighting these points allowed us to see where we actually have the breaks. And you can see already that there are quite some in this model, at least. And then we kind of optimize the shape to minimize the amount of these points, so that we know that the shape is as smooth as possible. That was basically the first part regarding the shape building and shape manipulation. And in a way, I have to be completely honest, we could have stopped here, in a sense that our constructors, as we later got to know, were actually asking us to provide them with just the surface, because then they were calculating the final Planck's division on their own. And also they were calculating the back structure. So we could have just provided the surface. But of course, as architects, we needed to see what the real material, like how the real material would behave, and also how the planks will look like in reality. And I think that was kind of the largest challenge behind this whole project, because building the surface was relatively simple, but then the next step came. So let's see. Let's get back to the presentation. So the realization part, it kind of consisted of, I'd say, like 4 small tools that we've developed. The first one was, of course, the Planck's division. We had to come up with a tool that will divide 2 different parts, the cones and the top part of the ceiling, into different directions of the planks. You can also see that in this image, this is actually a photo of a mock-up that was made after we've designed the building, to kind of check if the ceiling is actually working, or if the planks are actually working as we wanted. And the challenge here was that we had to stick with a single dimension of a plank for the whole surface of the ceiling. So we couldn't really divert to tapering. We also couldn't divert to the kind of traditional method of building such type of surfaces, which I think I can only call as a parametric bench. And I hope like some people actually understand what I mean. It's like when you're kind of splitting so nothing is actually bending. It's just like a CNC milled, curved, maybe plywood planks. But here we had to deal with just a single dimension of a plank, which was like 95 millimeters wide, and I think 3 meters or maybe 6 meters long max. And we had to only use this element to kind of clad the whole surface. So basically, there were some certain rules which were applied to how the planks will be positioned on the ceiling. The main rule was that for the surface on the top, the planks are just going horizontally. And then for the cones, they are always going on the perpendicular to the bottom curve of the cone, which resulted in this fanning, which you can see actually in this screenshot provided. But we're kind of also dealing with it. And one of the tasks was to optimize this bottom curve to be able to make the fanning as small as possible, so that the planks are actually sticking together as closely as possible. Then the next challenge came, which was basically the material limit. These planks, they had sort of limits of how far they could bend. That's just because of the limits of the wood itself, the wood that was chosen. Basically what we did, we also built a small tool that allowed us to check for the whole surface where the critical curvature is. So basically the curvature that is smaller than the requirements, and that the material, the wood, allowed us. As far as I remember, it was around 2 meters minimum curvature that we could allow for this material. And what we also did, we made some sort of a curvature optimization tool using Galapagos. that allowed us to actually double check really quickly if the parameters that we're using for the cones and are optimal in terms of how relaxed the surface of the curve of the cone is. And I think, oh yeah, no, there's one other thing that I wanted to mention here. And that's basically something that came into the design quite late, and that was the class check. Usually those type of checks are happening, of course, in the later phases and with very specific software that is actually allowing for like an automatic class check. But for us, it was not always possible because we always, like in that case, we would have needed to export this surface once again, like again and again, and then share it with someone in BIM so that they could check these clashes. So what we did, we actually inverted the process. We took the information from the advisors and we've built a super simple tool, and I will show you in a moment how it actually works, that allowed us to check those critical points that were coming a bit too close to the surface of the ceiling and were sometimes also sticking out from the ceiling, so that we could also readjust the initial ruled surface shape and eventually get all of those installations kind of behind this ceiling surface. No. Let's go to the to Rhino now. Oh yeah, wait, sorry, this is Grasshopper. We need Rhino. Where's Rhino? There it is. So let's quickly. I will quickly show how, first of all, the planks came to be, and we will get back to our first lovely cone. So basically, for the input for that, we used this surface once the cone surface was designed. And once we were actually happy with it, what we did, we built a small tool. And the way it worked was actually, it was taking the bottom curve, and then it was just positioning the planes perpendicularly to this bottom curve. I'll just do the, yeah. So you can see that it's on, should be on perpendicular. Oh, sorry, it's here. There we go. And basically what happened next was just a very simple intersection between the surface of the cone and those planes. And then through, once again, just a very basic extrusion, those planks were created. And that was actually already enough for us to see how the planks will develop. What was though quite important, as I mentioned already, was the optimization of this bottom curve. And we tried to work with the different curvatures here for the bottom curve to make sure that the planes at the top, and you will see it now, that they're not too far apart, so that this fanning is not too far from each other. So basically, there was this little tool somewhere here. Oh, I cannot really find it now. But what it did, it kind of just, oh, it will rebuild the whole thing now. But maybe that's even for better. It did. And you can see now it was changing the shape a little bit. Let's get back to what it was. So that was point one, basically just building the planks. What happened next, we just took all of those planks and they were put together, I think somewhere here. Let's see. Just a moment. Yeah. So basically we took these ones and then that ones, and you can see that it was kind of creating the planks for each and every cone. We also introduced this kind of division split in the middle to be able to minimize a little bit this gap in between the planks, which is also quite a nice thing to do. And in the end, we came to this result. And nothing is showing for some reason. Yeah. where we had all the planks kind of projected. And this way we could really evaluate how the curve would look like. We also had to work with a bit of different dimensions of the planks. So that was also possible to adjust from the very beginning in the script. Like there was this node that was defining like the plank width, the gap between the planks. And basically by changing all of those parameters, we were simply readjusting the whole surface, the whole kind of design from the very beginning to the very end. Then, as I mentioned, there was an issue with the curvature analysis and extreme curvatures in the ceiling. So what that was, we've built this tool that kind of converted the whole thing into a mesh. And that allowed us to then later check the curvature for every single point on this mesh and highlight here in red where the curvatures are critical. And these critical curvatures are basically the curvatures that were below 2 meters. And then we had to decide if we need to optimize them or if the construction guys could actually handle such curvatures. And another very nice tool that was used here was, as I mentioned, a small Galapagos script. Let me see if I can open it right away. Yeah, it's right here. I hope it won't crash. So basically, here it was kind of an extraction of one of the cones. And what we did, we tried to take the bottom curve here on the ground. Let's see if maybe it's a bit more clear. Yeah. So this bottom curve here on the ground, and you could we could move this point and that point, thus making the cone once again more relaxed or less relaxed. And there were quite some other parameters which I can tackle now, and I can show what was happening. So basically, for instance, here the cone became a bit more relaxed, and this made it a bit more tight. And here on the ground, if this parameter was moving, we could also move, kind of control this bottom curve. And then these parameters that were defining how the surface of the cone was looking like were used as a genome for the Galapagos tool. And as a fitness function, we used the amount of points with the minimum critical curvature, which was 2 meters. So we couldn't go less than 2 meters. And basically, if the curvature was lower than 2 meters, we had to readjust the script. So here I just quickly will show how it works. I'll just put the 1 minute runtime limit. And what it did, it kind of quickly checked the different parameters here and different shapes of the surface of this cone. And was kind of creating different combinations of these parameters to be able to find the optimum scenario where we have the minimum amount of small curvature points. Yeah, I'll let it run maybe for a minute because I'm just always mesmerized with how Galapagos tool looks like. And it's actually a very helpful and nice tool to use in a project, even for a small portion of the project. It doesn't have to be for the whole thing. Because here, for instance, we only used it for the parts of the cone that were the most visible and the most critical for us. So we didn't actually run the script on the whole surface. Yeah, I'm going to just stop it for now because I think it's kind of enough and proving the point, let's say. So basically, we did this. We found the solution with a minimum amount of small curvature points. And then let's carefully go back to the main model. And I will show how this curvature graph actually looked like in the end. What we did also, we made a small tool that allowed us to visualize these curvatures. And that's the image that I showed previously. And that's basically for the cone, we could check every point and see how the curvature is changing through with the height of the plank. Yeah, you can see it here. Kind of the larger the circle, the larger the curvature. And finally, as I mentioned, there is this very nice tool that is doing the collision. It's actually just a very simple box that was positioned in like one of the crucial points, and we had multiple of them all around the surface. And basically what it did, it kind of maybe I should just show the surface from here. It kind of checked if there is an intersection between the surface and this box. And this box was corresponding in the big model to one of the elements that was protruding. That was, I think, some sort of insulation corner. Yeah, right here. And then it was kind of all the time checking if there is a collision or not. And then if this panel was empty, that meant that everything is fine. And if the panel was, yeah, maybe we can actually try to adjust it so that it provides us with a collision. Let's see if it works. Basically, it will just tell me, yeah, there is an intersection. So please double check the surface. Yeah, there is a closed curve here, which means that there is an intersection. And that means that our surface is actually hitting through this box. And it was super helpful because we could quickly just model all these clashes and decide if we need to do something with this, with the model, relax the surface a little bit or not. So that was part 2. Basically kind of bringing the model to reality and visualizing mainly the planks to be able to see how the actual ceiling will look like. So not only the surface, but also the planks, and to later also provide the construction team with the guidelines of how we would like it to look like, where the dip should be, what are the crucial points in terms of intersections, also intersections with installations, to also be able to inform the construction team regarding the curvatures, so that both us and them are sure that the design that we made is actually buildable, so that we don't have to kind of ping pong these issues to each other. Now, finally, there was the kind of the third part of this process, which was the kind of extra tools. And that mainly had to do with the way we wanted to visualize the project and present the project. So one of those tools was actually the visual materialization. We were making a movie for this project where we wanted to show how realistic the panels will look like. And you can see here, for instance, that we have different textures for different panels. And funnily enough, it was quite a nightmare to try to actually map a real material surface to all of those planks. So instead, we just kind of really quickly separated those in Grasshopper in 5 different batches and created 5 different material mappings with 5 different brightness types for the wood. And it's brought a very nice result. And finally, yeah, that's just running. And finally, there is one other thing that you probably have already noticed also in this movie. The ceiling itself and this wooden surface, funny enough, was not the largest challenge that we faced during the process, even though it was quite a bit of a challenge. In the very early presentation, I found this interesting note, shiny golden letters on the ceiling. And when I came to the project, I was actually wondering what that was. So one day I realized that from the original design, there was this kind of idea of an artwork that was supposed to be placed on the ceiling. And I have to say that the artwork was quite radical, but what I was even more surprised with, that actually this whole idea of the artwork survived the 10 years of development of the project. And at some point, we actually had to make it. So the artwork was, the idea was the following. So The Hague is a city of rights and kind of the capital of rights of Europe. And the Declaration of Human Rights was supposed to be placed on the ceiling. So that's the first thing that you see when you're entering the city of The Hague, which makes a lot of sense. But not only it was supposed to be placed there as a text, but it was also supposed to be made in the shape of the world map, which came with some complications, let's say, because not only we had to create this world map and position it nicely on the ceiling, but also convert it all into real elements, like real physical surfaces, or at least curves, and then project this geometry not just on the surface, but on each plank, because we had to be sure that each plank has a certain amount of these words so that the text is still readable. And that was quite an interesting challenge. What we started with was actually trying to just position this map on the ceiling. And here there was a very nice connection that we came up with, which was basically something that I can call maybe Photoshop inside Rhino, or Rhino inside Photoshop. I'm not sure how to explain it a little bit better, but basically we're doing different tests on how to position the surface. How to position the world map outlines, and then transforming this into a mesh surface into the boundaries, so that later those boundaries could be transformed into the kind of lines of text on the blanks. So how it was working, it was actually, yeah, I think I need to open another file, and I have a little bit of time for that. Let's see, I'm going to open the artwork now. It might take a bit of time to actually load this model. But basically the idea was that there was just always a file that was connected to Rhino and Grasshopper. Yeah, there we go, nice. Now let's try to add the artwork here. So what was happening? Just a second. We need maybe like five seconds for the script to run. Yeah, there we go. So what was happening here? And I think I need to turn this one off now, just from the very beginning, and also this one. So we're trying to find the optimal position of this map on the surface. It could only be positioned on the horizontal planks because it couldn't actually go down on the cones. So we were always working with this image that was projected, and later this image was converted into a mesh, and the boundaries of this mesh were calculated. And then this thing was kind of converted into, into the blanks. I think I will be able to see it here. Yeah. Yeah, you can basically see it. And this one, sorry. So also need to hide. Yeah, so they were converted into these blanks, and these blanks were actually corresponding to the horizontal surface of the ceiling. But what was actually even nicer, let's say, is produced us with this result, where all the words were later projected on these blanks. And you can see how it looks in reality. It's like this very nice curved text in the shape of the world map with the Declaration of Human Rights listed on it. But what was even nicer was actually that in Photoshop, we were always able to create some sort of different types of mappings. And then if I were to export a different image, let's say, yeah, we'll say, hi, Rhino users. And then I would like to export it, and I will save it with the same name. It will need some time to rebuild, but I think we'll be able to see, yeah, kind of the result that we wanted. I think some words were actually cut out because they were just a bit too close to the boundaries. But in general, you can see this is the greeting, although it's a bit it's actually mirrored because we had to work with a mirrored text. So yeah, it was actually a very nice tool, and it was actually quite a bit of fun to develop this sort of small artwork challenges and to try to define how to better address them. Diving even deeper into this whole world map shenanigans, there was also a bit of an issue with how the letters should work, and that's where Rhino actually helped me quite a bit, because you could, and actually Grasshopper, because you can just introduce a very small script in Python that would solve all the issues for you. So basically, I think you've all, like people who used at least Illustrator, they've all faced this issue one time or another. Basically, when you have a full square it's filled completely, but when you have two squares, it will only fill the boundaries. So basically, apparently the letters, they work the same way. They have the so-called homotopic equivalence classes, which I got to know only while I was working on this project. But that basically means that different letters, they have different amount of holes, which needs to be counted while working on creating something that will be later cut out on a laser cutter. And in order to do so, I was just able to implement this small Python script in my Grasshopper, which was dividing all the letters into the different lists and creating the correct letters. And then later, how the script worked, it actually just took the planks that we've just seen and it placed the sentences on the planks. And then each word was mapped with a length of the plank that it could be positioned on. And basically then each word was corresponding to a certain plank. And that's how the design kind of came to be. And that's how it looked like in the images. And I've already kind of shared how it looked in Rhino. So yeah, and basically that's the artwork. And I think it's going to be mounted quite soon, actually, letter by letter on this ceiling. I think my time is actually over just now. So I'm quite done with the presentation, and I'll be happy to answer your questions if there are any.
Thank you so much. It has been a really nice presentation. Many comments saying that it has been amazing, checking all the project and all the steps that you follow to achieve it.
Thanks.
I think it was also very interesting to see how smooth this huge file works. I think it's really very well worked on how you split all the parts to be able to work on it like that, because it's really complex with so many surfaces, all the parts of
Yeah,
the
it was always a challenge. I was always struggling with the kind of performance, and I was trying to optimize so that the script runs as fast as possible. And I think I managed to put it down to 7 seconds per iteration, like the full thing from the very beginning till the very end, which I was very happy and proud of.
Yeah, totally. I was really surprised because it's like really a lot of geometry, also with the letters, for example. So only that could make a huge problem for many users if you don't optimize it well. So congratulations for that.
Thank you.
I was checking before, there were some questions during the presentation, but I think you answered them when you were
Mhm,
explaining more and more. Most of them were about the curvature of the of planks,
mhm.
about the 2 meters curvature. If you can explain a little bit more about that, because I think most questions were about that they don't understand if the 2 meters curvature is to avoid a steam
Oh yeah,
bend. It's about the limit of the material, or what it is.
yeah. I can of course explain a little bit more about the curvature. So basically, I think the major issue of this project was budget. And if we had, let's say, unlimited budget, we could have well be without all those extra tools that we were developing, for instance, without the curvature analysis, because indeed, that's a very good point. Traditionally, you would just steam bend the plank in order to make the correct curvature. But unfortunately, we couldn't really afford this on this specific project. So we had to stick to the material conditions of the wood that we're using. And basically, we had to just make sure that the wood, and that's the image that you see, I think here somewhere. Yeah, that's the one. So basically, this is what I was doing in the office. I just put my foot on top of this plank. That's exactly the plank that we're supposed to be using in the ceiling. And I was measuring how small the curvature of this thing is. And we also contacted the manufacturer, and we wanted to avoid exactly that. So we wanted to avoid the plank breaking. And basically, what we did was to be able to track where, in which points, the material won't be able to perform well enough, so that, because otherwise it won't be able to be fixed. because of course, like with an industrial nail gun, which was used for fixing all of these things, you can easily kind of mount the plank, but it will break sooner or later, just under tension. So that's exactly what we're using. And that was the stop part, let's say. And then the bottom part here, I hope you can see my mouse. This is also something very important. Since we only could use the planks of a certain dimension in width, we wanted to avoid kind of, it's as if you were making in a Grasshopper and the meshing for the surface is going down to low, and then you can see all of those kind of rigged edges for the curves. We wanted to avoid exactly that, but in real life scenario, let's say, and just to make sure that the planks are going nicely in a very smooth surface around the curve of the cone. So I hope this answered the question.
Yeah, I think so. Thank you so much. There were some others, but as I said, probably word before, you answered them already during the presentation. So I think it's quite completely answered that question about the curvature of the material. The other one now that I was checking from Hendro Triantoro is how did you manage big environment of Grasshopper script? Have you ever lost on your script project? Any tips for labeling or numbering? So not so much about the project, but about how you work with Grasshopper and how you organize your script.
Oh yeah, that's a very good point. Well, I'm always trying. I think it's easier to just show the screen. Oh, that's not the right one. Just a sec. I'll switch to the right model so that we see the script, and I also just put it on the block so that we are like it's not performing. So basically, I have to say that this script I made, I'd say 4 years ago. So it's not the cleanest of my scripts. But indeed, it's always an issue with a script that are getting too messy, and especially for such heavy and complex scripts like this. Basically, if I select everything, you'll see that there is way more spaghetti happening here and there. But I'm using quite a lot the very nice tool. I'm not sure how it's called. I think it's called telepathy. Yeah. So basically, that tool allows you to link certain parameters and then create, based on these parameters, yeah, wait, maybe it's just a bit easier to show how it works and yeah, like this. So basically, it allows you to avoid all the spaghetti because then you can just select from all the keys that you've created and it will just pass a different parameter to this node. So that allows me to eliminate kind of the 90% of spaghetti that I'm working with. And the rest is basically grouping. I think that's something really helpful. I'm also using quite a lot a tool that's called big nicknames on the groups from Sunglasses. This is super helpful because it kind of allows you to see right away where different parts of your script are. Because usually when you're naming a group, it's just like this tiny, tiny thing up in the on top of the group, and it's like impossible to see it. And colors usually also don't help because that's like sometimes you're just kind of too lazy to set up all the colors. So this helps. And I think the third thing maybe to kind of manage the complexity are the clusters. I'm using quite a lot of them. And I think if I were to explode all the clusters that I have in this project, it will be just like a complete mess. Clusters not only help as an analog of functions in real programming, but they also help organize certain things. Like if you see that something is repetitive, or if you see that something just takes too much space, but you actually don't need this whole thing. So basically just cluster it and have it somewhere. I was always trying to put the names of the clusters, but I think I kind of, in the middle of the process, I failed. So just simple clustering. Yeah, and that's basically how my script is organized. And yeah, I mean, basically all the parameters that I used are usually kind of stored somewhere separately on the left. And like this is, let's say, a script that I cleaned up a little bit also for the workshop, for the webinar. But usually I also use kind of this zone, let's say here, as sort of a messy zone where I can do all the shenanigans and kind of store all the things that I don't need for the project. Yeah, so I hope this also answers the question.
Yeah, exactly. No, I think it's really nice organized, and it's also really interesting how you have the things that you need enabled or visible or not.
Yeah,
But it looks like if someone else takes this script, they can see quite easily how it's organized and where are the important things and where to touch it.
yeah.
Um, yeah, it's a comment from Andrea Butarini, but not a question actually, but he says, great project and presentation. This is a perfect example of the parametric mindset. Designers who haven't embraced this logic of often miss how a sequence of simple interconnected steps can define a form and resolve complex geometry challenges, achieving results that are simply out of reach for traditional static design workflows. I think it's really interesting because it's, as I was saying, it's really interesting that you don't uh, manage the roof only as a single geometry, but you have separate parts. Also, in Grasshopper, for example, the part that you saw with Galapagos is a
Yeah.
different part inside another part of the entire roof. So it's quite interesting how you divide all the processing into simple, smaller steps, and that's really how it works and how it's possible to achieve this kind of complex projects.
Yeah.
Um, I was checking. There was another question. Um, Let me check. There are so many now that I'm quite lost. Um, there were some questions again about if it has been recorded. I'm recorded it and I will try to upload it to our YouTube channel probably tomorrow morning. And I will send an email to everyone who has registered. So will be able to check it tomorrow. Um, Okay, Marcos Navarro is asking more a technical question. If there was a minimum spacing between nails to avoid cracking of the planks.
That was not, well, I mean, yes, I can actually show you maybe in a presentation really quickly because there is a nice photo of how it's being constructed. We didn't really calculate for that, but you can see here that basically each and every plank is being held by just one nail, let's say, and
Mhm.
it's just, maybe I'm a bit wrong, it might not be a nail, but a screw, but basically, yeah, it's just kind of one screw that was hitting the plank. And you can see that, for instance, for this bottom part, we have one at the bottom, one in the middle, and one at the top. And I think for this top part, there should be a little bit more, but basically the back side, this back structure, which you can also see here,
Mhm.
is divided into 1 by 1 meter. And that's how, oh, sorry, 1.1 by 1.1. And that's kind of the minimum distance between the nails that allows for them to not crack also.
Okay. Yeah. No, it's really cool to see this image. Um, the other one is how did you check the structural integrity? If you have performed any structural analysis
No,
of this
unfortunately
part.
not. We haven't. We had a consultant, a very nice consultant who was doing that with us. I was very eager to do that, to be honest, but I didn't, to be honest, have enough experience to actually. I mean, I'm not a structural engineer, and we didn't have any people in the office who could do it, so we had to outsource it. But they made an amazing job doing that. I was actually also just so surprised how they managed to build this whole thing and to calculate all the loads. But yeah, someone else was doing it. So
Okay. Correct. There's another question that I think is quite interesting. Is what was the documentation for that the construction team followed, or how did you manage to
oh
build it?
well, I don't really have access to that right now, but funny enough, those were so basically the thing consists of two parts. And there were like produced actual drawings, like technical drawings for how to build it. And this back structure, this one, was CNC milled. And then basically on each plank, I think there is, on each kind of this structural element, there is a code, from what I remember, which kind of tells you where to position it, from which parts of the ceiling, from which cone it is. And then this thing on the right is, even though there is, of course, like a technical drawing for this one, it's actually placed now on the construction site one by one, and it's a lot of manual labor. So I always imagine this kind of Michelangelo style of type of work of one person. Well, you can actually see it also here in the construction drawings. There are just two people on this kind of construction thing, putting the planks one by one after another. So there are technical drawings for this. There is a very, very precise I don't remember the name of the software, but it's not the Rhino software. It's something that is used in kind of in the later phases, like something like a BIM model, let's say. A very, very precise model with all the planks modeled and with the back structure modeled. And then this back structure is CNC milled, put together with code and everything, how you would usually put together like this parametric bench, as I call it. And the planks themselves are kind of manually placed, but following this model, but not precisely. So I would say that the ceiling itself, in the end, the planks, they will not correspond to any of the technical drawings per se that we have, because they have to decide on site where to cut them.
Okay, I think that's all. There are many comments saying thank you.
Yeah.
That it has been really interesting and really inspiring. So thank you so much, Arsenii, for the presentation and for showing the project. Thank you, yes, to everyone who watched it. I think we were like 200 online. So yeah, I will prepare the recording as soon as possible, because I think many people is asking to watch it again and to see all the details. So thank you so much. Have a nice afternoon or
Thanks a lot. Yeah,
day.
thanks a lot, everyone, for watching.
See you. Bye bye. Thank you.
Bye.
Bye.